So this is Newton's law of gravitation that we have discussed so far. The force between 2 point masses is directly proportional to the product of masses and inversely proportional to the square of the distance between them. F is equal to g m1 m2 by r square, where g is universal gravitational constant. Now let us define what weight is, though we have done it in earlier class also. Weight means the gravitational force of Earth. So if I take it as Earth, I am taking it spherical, and there is an object of mass is small m. So what is the gravitational force acting between them? G m1 m2 by r square. Let me be the mass of Earth. Let us take me as its mass and radius be re. So this is the radius. A very small object kept onto it. Actually, in comparison to the size of the Earth, all objects that we use in daily life, they have negligible dimensions actually. So G me m by, what is the distance between them? It's again re, so re square. This is the gravitational force on an object of mass m on Earth's surface. And Newton's second law of motion, F is equal to ma. This is the force, so it should be equal to m into a. For gravitational force, the acceleration is gravitational acceleration, so we can use it as mg. So the weight mg that we have used in earlier topics, this is that m into g. So m is this, so from here we can get the value of g as g me upon re square. So the weight of an object, gravitational force, which is g me upon re square, and from here we get the value of gravitational acceleration too. And if we substitute the value of mass re g, we get the value of g roughly 9.8 meter per second square, though it's not a universal constant. We will do that, it depends on many factors. Rather, we can find out this g from different methods also. We can drop an object from certain height and use second equation of motion, s is equal to ut plus half at square. If I drop it, f is equal to half gt square, we can find out the value of g from there. And substituting g here, I can calculate the mass of Earth also. Okay. But if it is known, then this is the value of g, gravitational acceleration. We used to take 9.8 only in earlier topics, but see, we have taken a very, the only force that we have taken is g mem upon re square. Though the fact, so this is the value of g on a flat non-rotating Earth. Because if we take into account, we will see all those factors. If we take into account that the Earth is rotating about its own axis, then there is another force also. This force will be able to provide the centripetal force, and then we can find out the value of gravitational acceleration from there. We will do all those things. Same way, I have taken that every point on it is at a distance of re. It may not be so. There are certain points on Earth's surface which are exactly on the surface, and there are some points, say mountains, so you have again a very large distance from even Earth's surface, so it means there are local variations in the value of g. This is the value of g for a flat non-rotating Earth. We will take into account all these things, that Earth is not flat, so the value of g will change. Same way, Earth is rotating, it's moving also, so about its own axis, so that will also affect the value of g. For the time being, you take it g as 9.8. Okay, 9.8 meter per second square, this is the value of g. Now when we are standing on a surface, if this object, if I take what is the net force onto it, so mg is towards the center, and then there is a reaction of the Earth's surface, and both of them are Same, so the net force is 0. I'm standing here on the surface, I don't experience any force because the net force is 0. There is a force in upward direction of the surface on which I am standing and mg downward towards the center of the earth. Net force is 0. Okay, if the surface on which I am standing is at rest, it's okay. One force is mg, another is r, and r is equal to mg. So if the surface is stationary, net force 0. But we can create some situations in which the net force is not 0. That is, the surface on which we are standing, it may accelerate up and down. And show you an activity. If we stand on a weighing balance and we move up and down, stand on your toes and then again come down, stand on your toes again and come down, and see the pointer. Your weight is same. If we go by it, that F is equal to mg is equal to g MEM by r square, our weight is not changing actually. But even then, that pointer is moving. So it means the effective weight is changing. The reaction is no longer equal to mg. It's possible to create the situations in which r and mg are no longer equal. It is equal when the surface is at rest. If the surface is moving with constant speed up or down, then again acceleration is 0, so r will be equal to mg. This is the case 1, this is the case 2. Now let me take another very interesting case in which the surface is accelerating upward. This is mg, this is r, and I am saying the surface on which we stand is accelerating up. You can simply do an activity, put an object and move it up, then down, up. When we take our hand up, it is heavier, and when I am taking it down, it is lighter. The object appears lighter. Rather, it may lose contact if I am moving my hand downward with an acceleration more than 9.8. See how the reading and how this observation is effective. If the surface is moving upward, is accelerating upward, not moving, the surface is accelerated upward with an acceleration a, it means there is a net force up. So r minus mg is equal to ma and r is equal to mg plus ma, or mg plus a. It means we feel heavier. The force of the surface on which we are standing is more than mg. So there is a net force acting in upward direction. The object appears heavier than its usual weight mg. And if it is accelerating downward, now r is up, mg down. I am saying surface moving downward. mg minus r is equal to ma. Surface moving downward, but not with constant speed. It is accelerating downward. So it is mg minus r is equal to ma, and r will be now mg minus ma or mg minus a. So now again the reaction will be different from mg. It appears lighter. What if the surface is moving downward with an acceleration of 9.8? ma is equal to mg in that case, r becomes 0. This is what we call as weightlessness, and it happens. If I move my hand downward with an acceleration of 9.8, then it is moving downward. It is also moving downward with an acceleration 9.8. It means they are just touching, but it is not pressing against it. And if I move my hands downward with an acceleration more than 9.8, then the contact is no longer there. Okay, so that is the weightlessness if it is moving downward with an acceleration of 9.8. Otherwise, r is not equal to mg if the surface is accelerating downward or upward. Stationary, they are same.